Hi all, this is Mr. Yeager for Honors Chem, and we are looking at stoichiometry today. Let me get rid of this little guy up the top. Go away. There we go. All right. And we are introducing stoichiometry today. If you have heard from other chemistry students, this is often said to be, oh no, the most dreaded unit in chemistry, the one that's so difficult, blah, 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 blah. All right. It's really not too bad, all right? If you understand the mole conversions, okay, grams to mole, moles to gram, all right, or any of those other ones, moles to particles, even though we're not going to have to use that as much anymore, we are pretty good. We are pretty good for this. I think we kind of make a little bit more. It is a little bit of a more multi-step type problem, and it will show whether you understand some of the other topics like balancing and writing chemical equations, all right? Obviously, if you have that all down, this is only, hey, an additional step and a couple different ways to play around with it. All right? So, what are we going to cover this unit? The office, right? All right. So, we got stoichiometry conversions. That's what I'm going to basically be covering in this video. We're going to go through mole to mass, basically being able to convert one compound to another. I'll get the actual definition on the next page. We're going to look at something called percent yield. So, when you actually do a chemical reaction, how effective, how efficient, I don't want to call it necessarily efficiency, I mean it's related to that in a way, but how good is the reaction? You know, you're expecting that you should create this, but do you get 100% of what you're looking for? You will see that a lot of times you don't. You get way less than 100%. All right? And then limiting reactants. All right? This is where, okay, you do mix two chemicals together, but you run out of one before the other, right? You know, if you're baking, we always say, what do you need of each of your ingredients? If you're missing one of the ingredients, guess what? Can you make what you want to bake? No. Okay? So that's what we're looking at with those topics. But again, today, in this video, is stoichiometry conversions. So, here we go. So the really new thing is what's called the mole ratio. Okay? So, what is going on with the mole ratio? So stoichiometry itself is a chemistry method to predict the amount of product that will form based on the amount of reactants in a chemical reaction. All right? So that is what this crazy stoichiometry word is it's helping us actually predict the actual mass, the amount that you should create, again, the amount that we should create when we do the chemical reaction. So this is where your chemistry teachers, you know, when I'm developing labs, I'm making sure you have the appropriate amount of chemical that we should then see this reaction occur. We know exactly what we're putting together with it. So we do have to bring back our chemical equations. I know we didn't have to do that so much in our mole unit. All right. We do have to get to writing and balancing them. But there's one basically new concept in this particular part, and that's what's called the mole ratio. Okay? The mole ratio is the ratio of chemicals involved in a chemical reaction. You actually have been doing the mole ratio. We haven't been talking about that. The coefficients in a chemical reaction, those coefficients are actually telling you the number of moles involved in the chemical reaction, the moles of each compound. So that's what we're looking at with those coefficients. Okay? The coefficients will tell us the moles. So you have an example I already have done here. Okay? I'm going to try to pull it up a little bit more so you can see everything. All right? So we have our balanced chemical reaction. We have 2H2 plus O2 yields 2H2O. Okay? And so you can see my coefficients. I have a coefficient of 2 hydrogens. There's no coefficient in front of O2, so that means it's 1. And then we have a coefficient of 2 in front of water. So in this reaction, we look at those coefficients, and the coefficients is the number of moles in the compound. So what we basically are saying is any of these three statements, or their inverse, if I kind of do them backwards, is true. That what we're saying is 2 moles of H2 reacts with 1 mole of O2 to form 2 moles of H2O. That is what we're always seeing. That is the ratio of the moles between two different compounds in a chemical reaction. So 2 moles will always react with 1 mole of oxygen, or the ratio will be 2 moles of, wow, I just said it out loud again. A 2-to-1 ratio of the moles between hydrogen and oxygen. I always need 2 times the number of hydrogen molecules, H2 molecules, to 1 mole of oxygen molecules to be able to have a complete chemical reaction on it. All right? Or I could say 2 moles of H2 form 2 moles of H2O, or vice versa. I could say 2 moles of H2O are formed if 1 mole of O2 reacts. All right? So that is what we are looking for there. That is the ratio that we're looking for. So if I said I had 4 moles of H2, I would need 2 moles of O2 in order to completely react the two together. It's still a 2-to-1 ratio. And that is the mole ratio we are playing around with here. So it's you know, in the end, it's nearly no calculations. It's balance the equation, and then you use those numbers, and we're going to use that in our conversions. Okay? So just look at the coefficients. We don't like to reduce, all right? So like this one in the middle here, here's some of our mole ratios that we would write out. 2 moles of H2 for 1 mole of O2. 2 moles of H2 to 2 moles of H2O. I understand I could reduce this to 1-to-1, but that is never going to be required. If I actually ask on a test, like what's the mole ratio, you could say 2-to-2, okay, between those 2 objects, okay? Because that's what you'd end up actually writing in your formula. If you want to reduce it to 1-to-1, good for you. Have a lot of fun. But all of those can then be inverted, okay? So right here, I have a couple examples where we just want to try to find the mole ratios, okay? The first thing, though, is we need to balance this, okay? So I have C2H6 plus O2 yields CO2 plus H2O. I would start with 2. I'm going to just put it, I guess I can put it in front of it. I'm going to have 2 C's, 2 C's, 2 C's, 3, I got 6 H's, so 3 times 2 is 6 H's. And then this would be 4 oxygens, and this would be 3 oxygens, so that's equal to 7 oxygens. Well, I can't get 7 on this side. What's my little rule? Erase everything, put a 2 in the front, and start over. Now I need 4 carbons, I need 6 waters, 12 hydrogens, and now I have 8 oxygens plus 6 oxygens equals 14 oxygens. So I need to put a 7 right there. So what would be my mole ratios? My mole ratios in this would be 2 moles C2H6 over 7 moles O2. That would be one of my mole ratios. Or vice versa. I could say 7 moles of O2 over 2 moles of C2H6. But I just leave it that way. Don't solve. This is not like, please solve this. It's not 3.5. You know, 7 divided by 2 is 3.5. No. These are the conversion factors, just like we've done with molar mass, just like we've done with particles. Okay? If I said, what's the mole ratio between oxygen and carbon dioxide? That would be 7 moles of O2 to 4 moles of CO2. Okay? So they go together. All of that goes together with it. Okay? All right, let's just look at the other reaction, because we're going to see this a lot. You obviously have to do this in every single problem. In my second problem here, I got 1 BA, 1 BA, 2 CLs, 1 CL, so put a 2. Now I have 1A, 2A, NAs, sorry, not A's, NAs, and then 2 F's and 2 F's. So I said, what if I said, what's the mole ratio between BaCl2 and BaF2? Well, it would be 1 mole BaCl2 and 1 mole BaF2. Okay, and there you go. Good. All right, I could say 2 moles of NaF and 1 mole of BaF2. It's just all about the coefficients. It's all about the coefficients with it. So, like I'm trying to push a bit more with this year is, again, or any year, is what is the purpose of all this? Okay? What is the purpose of the mole ratio? You now have the ability to convert from one compound to another compound. This is our way. In the prior unit on moles, we focused on only one compound the whole time. We converted the mass of that compound to moles. We converted that mass to liters, mass to particles. But we always stuck with one compound. Now we can convert between the compounds. Okay? And so this is also the first time that we will see that mole, when it's with a mole, when you have a conversion where it's mole and mole, you can have a number other than 1 with the mole. I'll go over that when we start doing some calculations. Okay? So, using that, we can get to the calculations. Okay? When we do stoichiometry, while we primarily are interested just between the conversion between moles and mass. Moles and mass. All right? We don't need to worry about liters. We don't need to worry about particles or anything else like that. We can just convert between moles and mass the majority of the time. Okay? You can use stoichiometry to figure out any of those other things like you see I've written down here. You can find the volume, you can find the number of molecules involved, but that's something that's, I mean, liters is sort of useful if we're dealing with gases, but if I'm using solids, I need to know the mass of that solid. Okay? So, how do we do stoichiometry? First step, write a balanced chemical equation. Okay, a balanced chemical reaction there. That's the first step, always, always, always. We just need to be able to do that. Okay? So make sure that you are all set there. Okay? From there, we kind of have, these are all in its way the same, but we kind of break up, hey, are you going to go from mole to mole, and that means mole of one compound to mole of another compound, or are you going to go from mole to mass, mass to mole, or mass to mass? All of it is kind of the same process, it's just it might involve more and more steps. Okay? So we start off with mole to mole. We want to convert from one compound to another compound. That's what mole to mole means. Okay? So we have our first example here, and I mean I'll do some other examples as well. Okay? That I go back to my hydrogen-oxygen reaction. I balance the reaction, and then if I have the problem itself, it says if you have 3 moles of H2, how many moles of O2 react? What you do, and I think this will be better when I do some additional problems, because again, I don't really like the way, I'm usually a little bit more strict. I like to see that we're using train tracks or like the fraction method. But the idea here is, I'll even rewrite this, is if it says, I have 3 moles of hydrogen, how many moles of O2 react? Always start, just like we did before, start out with what's given to you. So I start with 3 moles of H2. Okay? I'm in the mole. The mole can be converted to anything else. It can be converted back to grams of hydrogen. It can be mole to liters or particles of hydrogen. Or now with my mole ratio, I can convert to another compound. So that's what I'm going to do. I'm going to do a mole ratio. I'm going to do moles of H2 on the bottom because that's what I'm coming from, and moles of O2 on top. Now where do I get these numbers? I look at the chemical reaction. I look at the coefficients, and all I do is write those down. They will be whole numbers. So O2 is 1, H2 is 2, and there's my calculation. And that's what's going to happen. I am converting from moles of H2 into moles of O2. So what would this be? 3 times 1 is 3, divided by 2 is 1.5 moles of O2. So if I have 3 moles of H2, it will react with at least 1.5 moles of O2. Like, it will react with that much. And you can see I still have my, 1 to 2 or 2 to 1 ratio there. Okay? Again, it depends on how you're kind of perceiving it. All right? But that's basically it. So you can see my other example down here. I'll actually rewrite it up here again. In the bottom one, it says how many moles of H2O are produced. I'm still using my initial number, 3 moles of H2. Because I'm in the mole, I can change it to anything else. I'm going to go from the mole of H2, and I want to go to moles of H2O. I can only change compounds through the mole, nothing else. And that's one of the mistakes I see people do. I also cannot find grams of H2O. I need to go through the mole first. So I go from, I look at the coefficients, 2 moles of H2O and 2 moles of H2. Well, in a way, what's 2 divided by 2? 1. I mean, I could do this as 3 times 2 is 6, divided by 2 is back to 3. So I would get 3 moles of H2O in the end. All right? So that is the process of mole to mole. That is the process of mole to mole. So I have this little flow chart you can see, but I'm going to rewrite this over here. Okay. And basically what we are going to be looking at, this is the step we just did, is we can go from 1 mole of a compound number 1, CPD stands for compound, to mole of compound 2 using the mole ratio. That's the only way we can do that. From there, I could expand this, and this is what I'm going to show you by doing some other problems. I can convert moles of compound 1 back to the mass of compound 1. The chart shows that technically I can change this back to particles. I can change it back to volume as well. Okay? But the main course we're going to be looking at is mass to mole, which is through molar mass. I would use the molar mass to convert between mass and mole. Well, guess what? The exact same thing is true on the other side, but just with a different compound. So kind of, it's going to take a little bit longer because now in a problem, you might have to find 2 molar masses. All right? You might have 2 molar masses involved. Just make sure you keep it straight. Okay? And one of the biggest things I will recommend, and I'll be trying to show you as I do these problems, is write the compound with it this time. Maybe in the mole unit you stopped writing the compound because you knew which one it was and you stuck with that. We will want to write which compound I'm working with so you don't switch up molar masses. But again, the new step is this one right here. This is last unit. This is last unit. Okay? We know how to change moles back to mass of individual compounds. Our new step is this mole ratio in the middle. So if I want to change anything to something else, again, it always goes back to the mole. All right? So I have some example problems we're going to do. Okay? So we have this one. How many moles of hydrogen gas are needed to react completely with 2 moles of nitrogen gas? You can see the coefficients are already given. Sometimes I do that, so pay attention. Okay? So we're already balanced. What am I starting with? 2.0 moles of nitrogen. Okay. What am I trying to go to? Moles of hydrogen. So if I go back to my chart again, chart, I'm starting right here, and I'm going to moles of compound 2. So how many steps is this going to be? Just 1, the mole ratio. Okay? It's not a bad thing to write this little chart out for you so you can be like, this should only be 1 step. So I'm in moles of N2, so what am I coming from? Moles of N2, going to moles of, what do I want? Hydrogen. Sorry, hydrogen. Please say it's not deleting already. All right, so nitrogen has 1, hydrogen has 2, so 2 times 2 is, it's deleting on me, that's okay. 4 moles of hydrogen. 4 moles of hydrogen. And there you go, there's your problem. Okay, and we're all done. Make sure you have the correct sig figs. Okay, all right, let's try another one. How many moles of aluminum are required to react with 5.09 moles of oxygen? So this one, and sorry that's going to erase on us some, we'll deal with it. Okay, I got to balance first. 1 Al, 2 Als. I already know that I'm going to need more than that because I have 2 and 3 oxygens, so I need to raise that to 6. All right, and now I have 4 Al. So, how many moles of aluminum are required to react with 5.09 moles of oxygen? Okay, so what I have here, oops, make sure I write the unit, moles of oxygen. I need to convert from moles of oxygen to moles of aluminum. This one is 4 to 3. Sorry, I can't necessarily do that off the top of my head. I want to get my work in front of me here. Okay. And this should come out, you'd multiply by 4, divide by 3, and this comes out to 6.79 moles of Al. And there you go. There's your process. Again, I'd encourage you to cross out your units. If you have the same unit on the top and on the bottom, cross it out so you know that you're getting the final product that you really want. Okay? So that's mole to mole. So that's going to show up in every single one of these problems. So now let's try a different one. Okay? What I'm looking at here is how many moles of aluminum oxide can be formed from 1.5 moles of aluminum. Okay? All right, sorry. Put this right here. There you go. Okay. sorry, I'm trying to find the right page on my things here, so just a second. I have 1.5. Oh, okay, I am on the right one. There we go. All right. So, first things first, I got to balance this reaction. All right. So what I run into here is I got 2 ALs and 1 AL, but I'm going to see in a moment that's not going to really work. Let's actually get the. I mean, this one's definitely a little tougher. I guess we'd start with that. I'm going to put what I would be doing with this. It would be 2 AL, and then I'd have 6 BRs, so I need to put 3 there. But then I have 2 and 3 with the oxygen, so I need to raise that to 3 and this to 2. So I need to put the aluminum back to 4 now, because I have 4 aluminums, and now that's 12 bromines. Okay. All right. So if I look at this, what I have would be, I start with 1.5 moles of aluminum. Okay. I want to find grams of aluminum oxide. So on this one, basically what's happening is I'm starting with moles of compound 1, but I want mass of compound number 2. So what's that telling me I need to do? I need to go from moles of 1 to moles of the other compound using mole ratio, and then I can convert that compound back to mass using its molar mass. Okay? So 1.5 moles of Al, I'm coming from moles of aluminum and changing to aluminum. Oh, I'm actually finding how much aluminum bromide reacts. Okay. What am I doing here? Sorry, I'm messing this up. Aluminum oxide. My apologies. I'm not reading it. I'm trying to go too fast. Aluminum oxide. Okay. So I'm coming from moles of aluminum oxide to moles of aluminum bromide. And I found out that aluminum bromide's 4, aluminum oxide's 2. That's the mole ratio, 4 to 2. I'm now in moles of, if I stopped here, I know how many moles of aluminum bromide would react, but I want to know the mass. So I need to go from moles of aluminum bromide back to grams of aluminum bromide. And this is where I see people make a little mistake that they probably weren't making in the last unit. This is our molar mass, grams per mole. When mole is with any other unit other than the mole, it's 1. Okay? That was our rule last time, so let's continue with that. It's not changing. Mole is always 1 unless you're looking at the mole ratio, mole to mole. So the molar mass of aluminum bromide is that is not correct. Oh, wait. I did it backwards. Ah, I'm so sorry, everybody. 1.5 moles. They're all sitting there watching this going, what is he doing? Aluminum bromide. You get to see mistakes this time. All right, so that's 4 moles of aluminum bromide. 2 moles of aluminum oxide. I don't know why I wrote it so far down. And then 1 mole of aluminum oxide. And this is 101.96 grams. I was looking at my work and I'm going, there's no way aluminum bromide is that little of a mass. So I apologize. I made 2 mistakes on that one. But there we go. Now we got it. This is a 2. So I would do 1.5 times 2 times 101.96 divided by 4. That comes out correctly to 76 grams. 76 grams. Okay? So again, each time, even though I kept on changing the compound, we had the right process. It would have been wrong because I would have been looking at the wrong chemicals. But we go from moles to moles, mole ratio, and then moles to mass, molar mass. Okay? Oops. Let's see if I can get this one correct now. Okay. So basically, same thing here. H2SO4 plus sodium bicarbonate yields CO2 plus sodium sulfate plus H2O. Plus H2O. Okay? All right. So for this one, okay, balancing it out, I have 2 H's, 2 H's. I have one SO4, 1 SO4, 1 Na, 2 Na. So I need to put a 2 here. Actually, I'm sorry, I have 4 H's, don't I? I have 2 plus 2 is 4,
Good morning, Rocco.
so 2.
If you were
Okay.
invited to the
And
leadership
sorry about that
meeting,
for a second.
please meet in the theater during
Yeah.
Bronco block. Thank you.
All right. Now you get to hear some announcements from school. Okay. So we got 4 hydrogens, so now I have 4 hydrogens over here. And then 1C, 6 O's, 2 plus 4, am I messing that up again? Not counting something right. Oh, yeah, I have 2 C's, so I need to put 2C there. So now I have 6 O's, 4 plus 2 is 6. 4 plus 2 is 6. All right, so for this one, I'm starting with 150 grams of sulfuric acid. I'm not going to make as many mistakes this time, okay? And I want to find the moles of sodium bicarbonate, so another compound. So on this one, I need to change this first to moles. So I'm going to go from grams of H2SO4 to moles of H2SO4. And again, since moles is with a unit other than moles, it's 1 mole. And the molar mass of H2SO4 is 98.07 grams. Now that I'm in moles, I can change to whatever I want. And I want to go from moles of H2SO4 to moles of, what do I want? Sodium bicarbonate, yep, NaHCO3. So this is going to be 2 from the coefficient to 1 from the coefficient, and that equals, in the end, after you calculate it out, 3.059 moles. And there you get your answer there. All right. Last one, quote unquote, the biggest one, mass to mass. So if I'm doing mass to mass on this one, I'm going to start in mass of compound 1, and I want to get to mass of compound 2. This is really the whole purpose of this primarily. I'm going to change from mass to moles of that compound, go from mole to mole, and then mole back to mass of the other compound. So you do need to find 2 different molar masses. So I got NH3 plus F2 produces N2F4 plus HF. Okay, plus HF. So if I have 1 N and 2 N's, that's 2. I have 6 H's. I need to put 6 H's there. And then I have 4 plus 6 is 10, so 5, so 5 F2. Okay? So if I look at this last one here, okay? Almost all done. Okay? It starts with 45.75 grams of ammonia. I need to change this to moles, so 17 grams of I don't know why I write NH3. NH3 to 1 mole of NH3. I'm now in moles if I stop right there. I'm going to change from moles of NH3 to moles of, what do I want? Dinitrogen tetrafluoride. There's 1 coefficient in front of N2F4 and 2 in front of NH3, and then 1 mole N2F4, and the mass of that is 104 grams in the end, something close to that. So here we go. This is the biggest any stoichiometry or conversion looks like, 3 steps, because I had to change from mass to moles, moles to moles, and then moles back to mass of the other compound. Everything cancels out nicely, that all I have left is grams of N2N4. I go 45.75 times 1 times 1 times 104, divided by 17, divided by 2, and this comes out to 139.9 grams. Okay? So, it should feel like it gets very, very repetitive, all right? I don't want you to discount this first step. Obviously, if we don't balance the reaction right, we're going to have an incorrect answer at the end. We could still do the whole process, but you're going to sit there and go, why do I keep getting wrong answers? We need to have that chemical reaction to start off with. But I hope you see the process that we're going through with it. Okay, I know this got kind of messy. We started with the new step of moles to mole of compound 2. Okay, if I change colors just so I can show this to you one more time. We can change between compounds using the mole ratio, and then from there, it's the steps we learned last unit where you can change into anything else, but primarily it's going to be all about the mass. All right? That's it. Sorry for my mistake on that one problem. Hopefully everything else is good, and have a great day.